Good morning. Thanks for joining our webinar today. The topic is Fluent CFD meshing.
All right. So what I'm going to be doing is I'm going to be giving you a quick presentation here on Fluent meshing. I'm going to start with kind of some basics of meshing and why Fluent meshing is good. And then I'm going to be doing a live demonstration so you can see Fluent meshing in action and see how the steps actually work. So to start, important point is that your mesh is important. If you have a bad mesh, you will end up most certainly with a bad solution. If your mesh is too coarse, especially in areas of a high gradient solution, you're probably going to miss some of the solution there and you're going to come up with the wrong answer. If you have too fine of a mesh, on the other hand, though, you will end up wasting computer resources and a whole lot of time solving for a finer mesh than you really need to. So ideally, we can be as efficient about this as possible. Another thing to keep in mind is the alignment of your mesh can sometimes be important, especially in fluid problems. If you have an area of your geometry where you know the main direction of flow, if you can align a hex mesh to be in line with that flow, that is kind of the ideal situation where you're going to get the best answer and capture all of that high gradient solution that you're looking for. That being said, sometimes we don't know the direction of flow, or in turbulent areas, the direction may be swirling and you're getting vortexes and things like that. And so it's not really possible. So we're looking for other element types that you can put in those situations to still capture the best and get the most accurate solution. Oops. So one of those difficult areas is the transition zone. This is the zone between your boundary layer and your volume fill. Now, traditionally, this has been filled with either tetrahedral or pyramid elements. Those elements work, but they're not always the most accurate type of element to put in there, and those type of elements require a high cell count. With these polyhedral elements that Fluent meshing offers, they are much larger than those elements, and so it reduces the cell count of your entire mesh, as well as they have also been shown to be as accurate, if not sometimes more accurate, than the traditional tet or pyramid transition zones. As an example of that, a test case was run. This was just what you're seeing here is a cross-section of the overall geometry to give you an idea of what the meshes looked like. On the left, we have the tetrahedral mesh. In the center, we have the hex mesh, and on the right, we have the polyhedral mesh. And as you can see from these cell counts, the tet mesh is much larger than the other two, being at 55,000 elements, while the hex and polyhedral meshes were at 8 and 9,000. So in terms of cell count, the tets definitely loses in this example. But as far as the accuracy goes, to get an idea of that, we can take a line right through the center of this cross-section and sample the solution at those points along that line. And looking at the graph, the green line is the tet elements in the solution across that line. And as you can see, the solution kind of jumps up and down, which of course is not what you want and would not reflect reality. Really, you would get more of a smooth transition here, which is what you would be after. The hex line in black is much better. It still has some angles and some back and forth on it, but it's quite a bit better than the tet. And then finally, the poly line is the most smooth one, which would most accurately reflect reality and what's really going on in the problem. So getting into Fluent meshing, I'm going to be going over the workflow geometry. The traditional Fluent meshing had a tree-based meshing method, which was much more advanced and not as easy to use. In version 19.2, they've added in this workflow, and this makes it much easier to learn. It really lays out the steps one at a time for you, and so it's just much easier to get into and really streamlines the process. So it's been a big advancement and really makes it much easier for people that are new to Fluent meshing to get into it. So some of the characteristics of Fluent meshing. It is embedded into the same user interface and the same window as the Fluent solver. So once you're done meshing your geometry, you just hit one button and it takes you directly into the setting up your problem in Fluent. It is able to read in CADs of almost any CAD program, and I'll be going into that a little bit more later. It can handle very large and very complex meshes, It is scriptable, but that's more of an advanced feature. I might show you how to do that initially, but I'm not going to go into that too much because it's more advanced, and this is going to be more geared toward the basic workflow and doing kind of an introduction into that. Yeah, like I said, the tree-based meshing had been geared toward more advanced users with a lot more control. You still have most of the functionality of that tree-based meshing in the workflow, but it's just much easier to use. All right, so moving on to the geometry. When you import the geometry, there are a few restrictions on it. Your geometry should be relatively clean, so you don't want any gaps or missing faces in your geometry. The solids you bring in, if you bring in solids, need to be watertight. And I'll go into that in just a second, what that means. Excuse me, you mesh it by surface meshing and then volume filling. So if you're familiar with the tree-based Fluent meshing, there was a wrapping step, and that step is now no longer needed anymore. So when you bring in a geometry from an external CAD source, so not SpaceClaim and not Design Model or any other CAD program you may be using, one of the restrictions is it has to be a single body if you import it directly. So what this means is that if you're using, SolidWorks or CATIA or some other CAD program, what you want to do is first import that geometry into either SpaceClaim or Design Modeler. Once you're in there, you need to turn shared topology on for all of your solid bodies. And also when you're in there, you should make any named selections you're going to be using later on before you bring it into Fluent meshing. Name selections from other CAD sources won't be imported when you import your geometry into Fluent meshing. So make sure you turn shared topology on and make any named selections you're going to be using in either SpaceClaim or Design Modeler. So going into the watertight geometry workflow. First off, when you start Fluent, all you have to do to put it into meshing mode is just check the meshing mode box. Pretty simple. And there is one kind of big drawback to Fluent meshing, and that is it only works on 3D geometry. So if you would like to be doing a 2D geometry, unfortunately you just can't do that in Fluent meshing as of now. When you get into Fluent meshing, the workflow tab is on the left side there. As you see over here, this is where the old tree tab, and next to it is the workflow tab. Once you get into the workflow tab, you have two options. You can either create a watertight geometry. When you select that, all of the basic steps will be laid out for you. It'll lay out all of the required steps along with some of the more common steps that you would want to use anyway, things like local sizings. Or you can create a new workflow, and when you do that, you just have to go in and add each step of the workflow manually by yourself. So I think the watertight geometry is a safer bet, especially as you're getting used to the steps and learning how to do this. So when you select watertight geometry, this is what pops up. Those are all of the different steps that you'll be going through. And below, at every step, when you go into it, the window below it will open up, and that is where you'll enter in all of your settings and numbers that you want to define that step. As you complete each step in the workflow, you will go from the yellow lightning bolt into a green check mark. You may also sometimes get the green check mark with a star if there's a warning, or the red exclamation point if there's some sort of major problem with the step. Hopefully you won't see too many of those, but they do come up sometimes. So as you go through the workflow, all of these steps are customizable. You can delete the step, you can rename the step, you can go back and edit a step at any point what you'd like, and you can also insert new steps, or tasks as they're called here. When you do that, whenever you right-click on a task and click Insert New Task, the steps that come up that are available are only steps that would make sense at that point in time. For example, if you've already imported a geometry, it doesn't make sense to import the geometry again, and so that step doesn't show up in the list of tasks that you can add. This just helps the workflow be more streamlined and more focused, and will prevent you from kind of getting lost in doing steps that don't make sense or don't add to your workflow, and keep you moving forward. As you progress through the workflow, you are able to save your mesh and all the work you've done at any point in time. So let's say you're halfway through the workflow and you need to stop for today, and you want to pick it up tomorrow. Anytime you can just go into File, Write Mesh, and that will create a file that will save any mesh that you've created as well as all of these steps. So when you open this file again, whenever you pick back up, you'll pick back up exactly where you left off with all of the steps and all of the workflow and all of the settings that you created last time already there, as well as the mesh that you created. So that's a handy feature for stopping and starting whenever you would like. Here's what the user interface looks like. At the top here, you have the ribbon. Most of the work will be in the workflow tab, not on the ribbon. It's not a ribbon-based workflow, but there are some handy features up there that I'll be going over when I go into the demo. Next to the graphics window on either side, you have a couple of toolbars. These are for helpful in selection and for zooming, panning, things like that. At the bottom, you have the console window. This is where Fluent will display any sort of warnings or errors you get, as well as you can put in any text commands. If you're more comfortable using text commands, that's where you enter those. But again, on the left side is the workflow tab, and that's where we're going to be spending where we're going to be focusing for the most part. So here's some limitations on the workflow. The first one is that it's available only in the standalone version of Fluent. If you go in through Workbench and try to open Fluent in meshing mode through Workbench, that workflow tab just won't be there. You'll only have access to the tree-based meshing. So it's something to keep in mind whenever you go through to Fluent in the standalone version. From there, of course, you can save your mesh and export it to somewhere else if you'd like, or go directly into Fluent solution mode. But you do have to open it in the standalone version. Some limitations on the CAD import. I already went through most of these. You have a single body only from other CAD programs, or you more likely what you should do really is it's easier to go into Space Glimmer Design Modeler, share the topology in there, and then import it into Fluent meshing. One note on name selections, when you make those in Space Glimmer Design Modeler, is that you can't group multiple bodies into one single name selection. So if you're trying to do a name selection that has parts from two different bodies, you can't do that. You're going to have to make a name selection for each body that's involved that you want to make a name selection for. When you cap faces in Fluent meshing, because you can bring in a solid by itself without the fluid domain extracted yet, but when you do that, when you cap the faces, like the inlets and outlets, you can't use edge loops to cap those. You can only use surfaces. So something to keep in mind. You'd usually be using surfaces to cap anyway, but just make sure you select the surface. If you're used to using an edge loop, you just realize you can't do that in Fluent meshing. Currently, periodicity is not directly supported in Fluent meshing, but you can do it with a custom journal task. That was a scripting I mentioned earlier that I'm not going to go into, but just so you know, you can't do periodicity directly, but you will be able to do it using a script. There's the curvature and proximity size controls. There are global settings for those. These are the same settings as there are in Workbench meshing if you're more familiar with that, but there are no local size controls for those. And similar thing with the boundary layer controls. You get basically one boundary layer, and that boundary layer will be assigned to your entire geometry. You can't specify, for example, a 3-cell boundary layer thickness in one area and a 5-cell boundary layer thickness in another area. You get, unfortunately, you only get one setting, and that's what how the boundary layer will behave throughout your entire geometry. It's also not possible to use different volume mesh types in different regions. So if you want say in one volume, if your domain, you want a tet-filled mesh, and then another volume you want like a hex mesh. You can't do that. Unfortunately, you get one volume mesh type throughout your entire geometry. And finally, meshing is available in serial only. You can't do parallel meshing in Fluent yet. So here's the basic steps as part of the workflow in Fluent meshing. You start by importing the geometry. Next, you will add your local sizings and then create the surface mesh. Then you describe the geometry and create your regions. This is where you would define your inlets and your outlets, as well as describe which domains are solid domains and which ones are fluid domains. Then you'll create the volume mesh, and then finally you switch to solution mode. So for the geometry import in that step, one of the important things to remember is the units you select. You have an option for which units you defined your CAD model in. This is kind of important because if you defined your CAD model, say using meters, and you go to import it and you accidentally leave it on millimeters, well, that 3-meter wall that you created in your CAD geometry is now going to be a 3-millimeter wall. So just keep that in mind and just make sure you use the same units that you use to create your geometry. One nice thing about this is sometimes it takes quite a while to import a geometry into Fluent Meshing because it has to facet the entire geometry on import. But once it does that, the first time, it automatically creates this PMDB file. This is automatically created as soon as you import a geometry. And this is just nice so that next time if you go to import the geometry again, instead of having to go through that process, you can import the PMDB file instead of your CAD file. And it just reduces the amount of time on import, which can be pretty nice. So after you've imported your geometry, you do a surface mesh. And this is required before any other step other than local sizings. You create local sizings, then you create the surface mesh. The surface mesh is pretty important as it kind of defines the volume mesh, what the volume mesh is going to look like. So because the mesh is created by looking at the surface mesh and then filling inward from the surface. The surface mesh is a triangular mesh. It starts out that way. When you go in to define the volume mesh, it will convert the triangles to polyhedrals on the outside and extrude those in as it defines the mesh. And you can do both global and local sizings, which I'll go over in just a second here. So when you add a local sizing, you define it using a name. You can define the growth rate. You define it as either a local face size or a body of influence. You define the target size. And finally, you select the geometry using either labels or zones. Again, zones are created automatically on import. Labels are the name selections that you made ahead of time. You can make as many local sizings as you would like, and these can be any combination of the face sizings or the body of influence. The local sizings are all soft sizings. If you're familiar with workbench meshing, you're able to change the behavior from soft to hard. In Fluent Meshing, unfortunately, there's only soft sizings. You can't make any of these local sizings a hard. And of course, you can also just turn this off and say you don't want to add a local sizing and just use the global sizing if you would like. So the difference between labels and zones. The zones, like I said, are created automatically on import of your geometry into Fluent Meshing. But on the left side here, you can see the list of the zone names, and they're not too coherent. They're not very intuitive as far as what geometry it's talking about, which is why I always recommend to make a name selection on any parts of the geometry that you're going to be using, either for a local sizing or name your inlets and outlets, all those sorts of things. It's helpful to have those all labeled ahead of time as a name selection before you import into Fluent Meshing. So a quick comparison here between the difference of a local face size versus a body of influence. On the left side, we created a local face size on this geometry. You can see it's highlighted in orange there. And on the right side, we created a cylinder that as a body of influence. And it's on the exact same part of the geometry, so we can compare them side by side. So this is what the surface mesh looks like. And of course, the same sizing of 4 millimeters was applied to both sizings. So this is what the surface mesh looked like. From the outside, they look identical because the surface mesh and the body of influence overlapped identically. But when we do a cross-section of the volume mesh, we can see that on the left side, that surface mesh the sizing wasn't applied to the volume mesh. Whereas on the right side, the body of influence, because it was a solid cylinder, it applied to every cell that's created within the body of influence is affected and has that sizing applied to it. So definitely something to keep in mind and is a really good demonstration of how powerful the body of influence local sizing can be. So after we've applied our local sizings, we create the surface mesh. And this is very similar in terms of the settings as it is in workbench meshing. You have the minimum maximum sizings, and of course these are all global sizings. You've already created the local, which do override any of the globals here if they're outside the range. But for here, this is the global sizings only. The curvature and proximity settings work the same way that they do in workbench meshing. So if you're familiar with those, it works the exact same way. And you have many more options here. If you clicked on advanced options here at the bottom, there are quite a few more options for customizing your surface mesh. Once we've created the surface mesh, we go into describing the geometry and creating our regions. Because you can bring in multiple different regions in terms of a solid geometry or a fluid geometry, this is where you describe that. So if I have only a geometry that consists of solid regions, I can say that. And if that is the case, I can then cap the openings and extract a fluid within that solid geometry. Or if not, I can describe that I have only a fluid region or a combination of the two. So once you're done with that, you go into creating the volume mesh. You start by defining your boundary layer. And as I said earlier, there's only a global setting for a boundary layer. So this will be the same boundary layer throughout your domain. Some of the defaults are here. It starts out at 3, but you can adjust that. That's usually a little bit low. I recommend going higher than that for your boundary layer thickness. And then you just select the volume settings. And there's 4 different volume settings that I'll go over in a second. This is for the volume fill within your fluid domain. Like I said, the boundary layer settings are applied to all fluid regions, and they are not available for solid regions. But those restrictions are only applicable to the workflow. If you go into the tree-based tab, you can, that's where you can define those if you'd like. So this is what the different volume fills look like. On the left side, you have a couple numerics here. You have the size of the mesh and the minimum orthogonal quality. So this is just a sample geometry. When using this, using a polyhedral fill, you get 4.7 million cells and a 0.15 orthogonal quality. This is polyhedrals as both the transition zone and the volume fill. And here we have the polyhedrals as the transition zone and a hex fill within the volume. And the cell count is slightly higher with about the same orthogonal quality. Next, a hex core mesh. So here you have the hex cells as the volume fill, and your transition zone is tets and or pyramids. In this situation, it's probably pyramids. And you can see the cell count actually tripled from the polyhex core cell method. Finally, if you have an entirely tetrahedral cell, both in the transition zone and in the volume fill, again, you have just under 20 million cells, so much higher than the polyhex core or the polyhedral cell count, with also a slightly lower orthogonal quality. So that's it for the presentation. I'm now going to give you a live demo so you can see what it's like to actually see this in action. Let me make sure I'm showing the right thing here. Looks good. Okay. So here we are. So again, this is the ribbon. Some options up here I'll show you about. This is the console down here. You have your toolbars on either side. And over here you have the workflow and the tree-based tabs. So if I start in workflow and I go to watertight geometry, immediately all of these steps are created. And again, these are the most important steps, the ones you'll always use. And a lot of these are steps that are required, like things like importing the geometry. So again, I make sure I have the correct units, which in this case is going to be millimeters. I click on the little button here, and this will open my window here so I can navigate to my file. So if I go in here, I open the PMDB file since it takes a shorter amount of time than opening the original CAD file. Should just take a couple seconds. And here's my geometry. So this is what I'm going to be working on. This geometry we're going to be using 2 inlets, one inlet here, a secondary inlet here. The flows come in, we'll mix, and then this is going to be my outlet. So if I go to add local sizing, I say, yes, I do want to add a local sizing, and I'm going to be adding 2 local sizings, one of each. So we'll start with the body of influence, and I just name it. We'll call it BOI 3 millimeters. I change my target mesh size to 3, and I make this a zone because my body of influence is a solid, so it's a cell zone. I did label it as BOI. That's my name selection and from my CAD, so that's already in here, and I just say add local sizing. As soon as I do that, the extra task here is set, and I can go back in here and edit it if I would like, or just delete it if I don't like this local sizing anymore for some reason. But if I go back to add local sizing, I can then create the face sizing that I'd like to do. And so this I'm just going to call face 3 millimeters. I'll leave the growth rate as the default. Go to local face size, also make it 3. And if I go into label, I can select face here. And as you can see in the graphics window, it is also selected. If I don't want to select it here, or maybe I didn't make a name selection for it, you can go in here and right click and it will select the face as well. It'll also show up here since I didn't make a name selection for it. hit add local sizing, and again, those are both created here with a green check mark, and now add local sizing also has a green check mark next to it, because I'm all done with that. So moving on to create surface mesh. First thing you'll notice is when you create surface mesh, your geometry is covered with these little red cubes. Looks like your geometry developed chickenpox or something. But these are for showing the global sizing of your surface mesh. So you can see the large ones are the maximum size, and then the smaller ones are the minimum size. So pretty helpful for seeing what size elements you're going to be creating. So if I click on minimum size here, it only shows the minimum sizings. If I can zoom in here, and if you'll notice, as I change these will be changed dynamically as well, the little cube previews here. So if I change this from about 1 to 5, those get bigger, about 5 times bigger. And then same thing here with the maximum sizing. I'm going to change this down to 20, and you'll see those change as well. I will leave the growth rate. Here's the curvature and proximity if you want to adjust those. And if you go under advanced options here, there's quite a few more settings that you can also adjust. I'm going to leave these all as default, but if you don't know what any of these things are at any point, one nice feature is if you come up to the top here, you can hit this little question mark. And when you do that, what it does is it'll open the Ansys help menu, or the Ansys help viewer, where you can look at the Fluent user's guide. Should open pretty quickly. There we go. And nice feature is it knew I was on the create surface mesh step, and so it automatically opened it into creating surface meshes page of the user's guide. So I can scroll down here, I can read about curvature and proximity, or go down and look at the advanced options that were below and get a quick description of any of those. So while you're first learning Fluent meshing especially, this little question mark here is definitely your friend. So I'm going to leave all those as default other than my global sizings, and I would hit create surface mesh. To save a little bit of time, I've already done that. And what you get after you create the surface mesh is this guy here. And so you can see it created a triangular surface mesh, and it applied my two global sizing, or my local sizings, sorry. One on this from the body of influence here, and the other from the face mesh, or from the face sizing I did on that surface there. So now that I've done that, I'm ready to go into the next step, which is describe geometry, as I'm just working down the tasks here through the workflow. So for me, I have not defined my fluid domain ahead of time, so I'm going to select the geometry consists only of solid regions. I will say yes to capping and extracting the fluid regions. I hit describe geometry, and it automatically takes me to the next step, which is capping those regions. If I'd selected a different option there, this step wouldn't be here. It would be whatever the next step would have been, which is pretty nice. It kind of does it automatically for you, really guides you through it. So by capping, the first thing you need to do is you need to select a name for each of your caps. So I created the name selection, so you can see here. I called my inlets just ins. So I will refer to the name of the capping as inlets. I will make them velocity inlets, single surface, and then you can just select ins. And then hit the capping feature, and it'll just take a second here. And what it does is it takes the surface mesh here and just expands the surface mesh across the opening to create a watertight seal on the opening, as you can see there. I did the same thing on the secondary inlet there. So next, there's a check mark here that I need to make an outlet first for this opening. So I'll call this out, say single surface, and I call that out 1. So hit enclose fluid regions, and it'll go through the same process of just expanding the surface mesh and filling that in. Once it's done with that here, just a second. Oh, I see what I did. So I made a mistake. I forgot I left my outlet as a velocity inlet. I don't want to do that. So you go in here, you hit edit, and it'll let you go back in, change this to pressure outlet, and enclose again, and now it should work. And one very nice feature, the reason I immediately knew that was a mistake is because it was green. In Fluent meshing, the inlets are, well, they're not here right now. The inlets are green and the outlets are labeled as red. You can change the colorings in the options if you'd like, but it's a nice way so that I can immediately catch mistakes like that. So the next, you go into create regions is the next step. And all this is just for diagnostic purposes. It just wants you to tell it how many fluid regions there are supposed to be. Simply because if it calculates a different number of fluid regions than you put in here, it will, send a warning to make sure that you when you update regions, you correct those, and so you have the same number of fluid regions as you want. And a solid region wasn't accidentally labeled as a fluid region. But I only have one fluid region in here, so I hit create regions, and it's automatically filling in that volume. Now what you'll notice is the solid geometry went away, and I'm left right now with just the fluid domain. And so the next step is to update those regions. So I just have two regions here, the fluid and the solid, that's not being displayed right now, and those are both labeled correctly. Now I only have one fluid region, but if you were to have a more complex geometry with multiple fluid regions, the automatic naming scheme here of fluid 0, fluid 1, fluid 2, etc. won't be very helpful when you go into solution mode. So you can double click here and rename this as, say water or whatever you want to name it as. And this will be very helpful when you go into the solution mode to set up your problem so that you don't have fluid 1 and 2, you have something a little more descriptive. So once those are all done, those are all correct, the solids are solids, the fluids are fluids, I hit update regions, and I'm ready to move on to my creating the volume mesh. So first you have the boundary layer settings. Here you have the same 4 settings as in workbench meshing. So if you're familiar with those, that's great. And again, advanced options, so you can go into more customization of those. And then same thing with the volume settings here. You can fill with, these are the 4 different types of volume fill cells that I went over in my presentation. I'm going to leave it as, well, not leave it, I'm going to change it to polyhex core because I think that's the most interesting type and most informative to look at. And another nice option here is mesh solid regions. So I brought in the solid geometry and created this fluid domain from it. Now, in a lot of times in an application like this, you might not care about the solid geometry anymore. So if you uncheck this, it won't mesh that. It will only mesh the fluid domain that you're interested in. For me, just to show you the mesh, I'm going to leave it checked. And then the next step would be to hit create volume mesh. Again, thanks to the magic of webinars, I'm able to fast forward that process and show you the already created volume mesh here. So again, as you notice, the triangles are gone. It's now created these polyhedrals on the surface, and those are extracted into the boundary layer and then the volume mesh that's been created. If I go up here, I can insert a clipping plane. This is one of the nicer features up here in the ribbon. And this simply does pretty much what you'd think. It makes a cross-sectional view of your geometry. You can slide this back and forth to show different cross-sections. If I leave it right about here so I can get that upper boundary as well, I then hit draw cell layer and it'll fill in the volume cells. And so I can look at what this looks like. I'm actually going to move it a little further back here. There we go. So this is kind of what the volume cell looks like. So you can see the boundary layer here. Remember, this is the solid. I decided to mesh the solid region. So this is the solid region here with polyhedral cells and no boundary layer. And then here's the boundary layer moving into the fluid domain. You have the polyhedral transition cells into the hex core. Looking at, if I move it back up a little bit so I can see this guy, let's turn that off. There we go. We can see the difference here. So this is the body of influence sizing I used. And you can see the cells, the sizing was applied to all of the cells within the body of influence, even all the way into the very center. Going down here, you can see my face sizing was applied to the face, but the cell size grew until in the center. And in fact, if I go back a little further, you can see the cells in the very center here are the exact same size as the cells throughout the rest of the volume. So that's very cool. The mesh looks good, but if you want to see a little more quantitatively, if you want to measure the quality of your cell, what you can do is you go up to the top up here and you go into report, and you can look at the surface. These are the face cells, so they just look at the surface mesh. Or if you want to look at the volume mesh, you can go into cell limits. And if you want to look at only the boundary layer, you go into boundary cell limits. But let's say I want to look at the volume mesh. And let's look at all of it, the fluid and the solid regions. I go into quality. My quality measure is going to be the inverse orthogonal quality. So I hit apply to that, and I hit compute. And right here, it measures the minimum, the maximum, and the average of your cell quality. So this is inverse orthogonal quality. So 0.79 is about a 0.21 orthogonal quality, which normally would be fine, but let's say you want to make it even better. What you can do is you right click on create volume mesh, insert new task, and hit improve volume mesh. And this allows you to change the cell quality, and it'll automatically try to improve the cell quality to whatever you specify. So it was 0.21. If I say put in 0.3, I just hit improve volume mesh. And in the background, it's just automatically remeshing. It's finding those cells between 0.21 and 0.3 orthogonal quality, and it's improving the quality of those cells until it's done. And now it prints out that the final minimum orthogonal quality is 0.31. So that's great. It even did better than I asked. So that's an easy way to do that. Another way, if you want to look at a distribution plot of your cells, you can go up here into display, plot, cell distribution. And this will allow me to plot the quality, again, in whatever quality you want to look at. If I just keep it as inverse orthogonal quality, I just say all of the zones and hit plot. And this will give me a plot of the quality versus the cell count. So that's a nice way, again, another nice way to look at the cell quality of your entire geometry, so you can get a better idea of what it looks like. All right, and so with that, I've created a nice volume mesh and Fluent meshing. Those are the basic steps. Again, there's a much more advanced features you can go into within the workflow, or the tree. You can go into much more advanced features, but these are just the basic steps that I wanted to go over.